Resistor is going to be the topic of this lesson in my new General Physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson, we're going to learn how to find the equivalent resistance of combinations of resistors in series and in parallel, similar to what we did with capacitors in the last chapter. And then we're going to learn how to find and calculate the potential drop, the current, and the resistance, as well as the power dissipated across these resistors as well. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now we will see some similarities to what we saw with capacitors here, but you will notice a very key difference, and you'll notice it pretty quickly. So let's start with the similarities first. So with capacitors in series, we said they had the same charge. Well, with resistors, their job is not to store charge, so they don't really have a charge associated with them, but they're going to have a flow of charge through them, a current through them, and that's what's going to be the same for resistors in series. The current flowing through them is exactly the same. So for capacitors in parallel, they had the same delta V across them, and that's still going to be true. There's still going to be what we call a potential drop across these resistors, and it will be the same for resistors that are arranged in parallel. Now, how you identify resistors in series and parallel is exactly the same as how we identified capacitors in series and parallel. And so if two resistors are on the same pathway, they are in series. And again, it's hard to identify things that are on the same pathway until you know what it looks like to see things on alternate pathways. And that's what's going to be true on this one right here. So we've got a junction right here and right here. And you could look at current leaving the positive terminal of the battery and hitting that junction. And now we've got two options. That current can take a right and go through that resistor to get to this other junction right here, or it can go straight on and around the loop here to get back to that junction here as well. And we see that the 9 ohm resistor and the 3 ohm resistor are on two alternate pathways between those junctions. That's what makes them arranged in parallel. So, and the current going through one is not the same current that goes through the other. They don't have to have the same current. But again, between any 2 points in a circuit, regardless of what pathway you take, the potential difference will always be the same, and that's why they're going to have the same delta V here. So going back to series here, notice there's no junctions here. There's no alternate pathways. There's just a single pathway. The current that leaves the battery flows through the 9 ohm resistor, then flows through the 3 ohm resistor, and then flows back to the negative terminal of the battery, and that's the way it's going to work. All right, so identifying resistors in series and parallel, exactly the same as identifying capacitors in series and parallel. Now for the difference. So it turns out that when we had capacitors in series versus parallel, which was the easier one to deal with? And you might recall, well, it was in parallel. When you had capacitors in parallel, you could just simply add up the individual capacitances to get the equivalent capacitance and life was good. Well, that's not going to be true here. That's how actually you find the equivalent resistance for resistors in series. When they're in series, to get the equivalent resistance, you can just straight up add them together. Now, for capacitors, it's when they were in series that you had to add them as reciprocals. Well, now that's going to be true of resistors in parallel. When resistors are in parallel, that's when they're going to add as reciprocals. And so the process of finding that equivalent resistance, that's what's flip-flopped here when compared to finding the equivalent capacitance. And you got to get that straight. So we can see why that is as well. So if we look here, so the potential drop across these two resistors combined is just the potential drop across either one, or the sum of either one added together. And so in this case, we're going to find out in the next chapter that if you've got a 12-volt increase in your battery here around this loop, then the resistors are going to have to add up to a total of a 12-volt decrease. So, and we'll learn that more in the next chapter, but the big key here is that the total voltage drop across both resistors combined is the sum of the individual voltage drops off either one, which again don't have to be the same, but it's the same current going through each one. So if we look at this then, so we'll look at delta V for the entire circuit. Well, again, we're kind of envisioning that we can reduce this down to a single equivalent capacitor here. So in that sense, we have delta V equaling IR from Ohm's law. So we'd have I total times the equivalent resistance. And then for delta V1, we just have I1 times R1, if you will, sort of. And then for delta V2, I2 times R2. But we have to remember that there's not two different currents here. It's all the same current. The same current flowing through both resistors, or it's the same current flowing through the equivalent resistance if we kind of envisioned reducing it down to such a simple circuit. And so in this case, this I, this I1, this I2, this I total, if you will, they're all the same I. There's no distinction that needs to be made here. And as a result, because they're all the same current, that's going to divide right out of the equation. And it just leaves you with the equivalent resistance equaling R1 plus R2. And that's why they just straight up add when we have resistors in series. Now, when we look at these in parallel, so in this case, they're going to have the same delta V through these resistors, but it's the currents that are no longer going to be the same. And again, if delta V equals IR, then if you rearrange and solve for I, it's delta V over R. And so it turns out that the total current of the circuit, if you kind of reduce this down again to a single resistor, single equivalent resistor, if you reduced it down, so the delta V across this is the delta V of either of these as well. But the total current going through here is the sum of the current going through each of these. And you kind of think of the current that's going around this circuit that's leaving the battery and hitting this equivalent resistor is the same current leaving the positive terminal right here. But once it reaches this junction, it splits into two parts. Part of that current goes through the 9 ohm resistor, part of that current goes through the alternate path through the 3 ohm resistor. So, but the total current that left the battery terminal here, so is equal to the sum of these two individual currents. And that's going to be similar to one of Kirchhoff's rules that we'll learn in the next chapter with more complex circuits as well. But the big thing here is you should see that the total current here, so passing through the equivalent resistance, if you will, is equal to the sum of the individual currents. And again, with delta V equals IR, you can rearrange that to find that I equals delta V over R. And so here we'd have delta V over the equivalent resistance. Here, delta V over R1 plus delta V over R2. And again, you might be inclined to be delta V1 over R1 and delta V2 over R2. But again, the delta V is what is the same for circuit elements in parallel. And once again, delta V is the same and can just divide right out of the equation. And we're left with 1 over the equivalent resistance equals 1 over R1 plus 1 over R2. And that's why for resistors in parallel, they add as reciprocals. Now, one reminder as well. So when you've got only two resistors in parallel adding as reciprocals, just like we did with capacitors in series adding as reciprocals, if there's only two, there was a shortcut. So, and very similar, we have that same shortcut of R1 times R2 all over R1 plus R2 gets you that equivalent resistance here. So, and again, that just comes from getting a common denominator in the process. Ultimately just ends up looking like this right here. It doesn't work for 3 or more resistors in parallel, but if you got exactly 2, which is the most common scenario, you can quickly find the equivalent resistance with a simplified formula. It comes in handy a time or two. Okay, so now that we've kind of defined some things, we've got a couple questions to answer about each of these lovely sets of resistors. What is the equivalent resistance of each circuit? And what is the current through each resistor in each circuit? We'll go from there. All right, the series case is definitely the easier of the two. Again, we can just simply add the resistors together to get the equivalent resistance and then work our way backwards. And so in this case, our equivalent resistance is just simply going to equal 9 ohms plus 3 ohms, and we can quickly see that it's going to be 12 ohms, which makes our life easy. So the equivalent resistance, done. Second half of the question, though, is what is the current passing through each of the resistors? And keep in mind, it's the same current that's passing through each of these resistors. And so we're going to work with the equivalent resistance and the voltage here on the same reduced diagram to find that current. And then it's going to be the same current that's going through both of these, similar to some things we saw with capacitors where it was the same charge here and at this level as well. All right, so we'll use Ohm's law again. So, and current is equal to delta V over R, which in this case is the 12 volts over the 12 ohms. And the math is easy, and that's 1.0 amps. And so the current flowing around through this equivalent resistance is the 1.0 amps. And if you work your way back up the diagram, that's the current leaving the positive terminal of the battery here, 1.0 amps, flows through the 9 ohm resistor, keeps going, flows through the 3 ohm resistor, and then returns back to the negative terminal of the battery. And so 1.0 amps is flowing through both of these resistors. Okay, parallel is going to be the bigger pain in the butt here because they add as reciprocals. And so in this case, we'd be doing the 1 over the equivalent resistance equals 1 over 9 ohms plus 1 over 3 ohms. And again, you could try to find the lowest common denominator between 9 and 3, which is 9. And to make that work, you'd multiply this one by 3 over 3. And you'd have 1 over 9 plus 3 over 9 is 4 over 9. And so the equivalent resistance would equal 9 over 4. You'd have to reinvert it. Ohms, and that's 2.25 ohms. You could have also used our shortcut here and done 3 times 9 over 3 plus 9. And that would be 27 over 12, which once again reduces down to 9 over 4. But there's our equivalent resistance, so far so good. But now we got to find the current through each resistor. And this is going to be a little more of a pain in the butt. And we got a couple different ways we might do this. So one, again, we can use Ohm's law, where I equals delta V over R, because we know the delta V across each of these. So in this case, between this point and this point, so is going to be a delta V of 12 volts. And you might be like, well, how do we know that, Chad? Well, again, I'm taking advantage of something that you're going to learn in the next chapter about Kirchhoff's law. But on any loop, the voltage increase of the battery, or batteries, as we'll see in the next chapter, so it's going to be perfectly matched by voltage drops across the resistors in this case, for simple circuits having just batteries and resistors. And so around this loop, if I got a 12 volt increase here, then I must have a 12 volt decrease right here. So same thing on the big loop right here. If I've got a 12 volt increase right here, then I must have a 12 volt decrease right here. Wasn't the case over here. Here the voltage drop on this one and this one combined was 12 volts, but here it's 12 volts on either one. And because we now know the delta V across either one, and we know the R value for either one, we can then use Ohm's law to find the current through either one. And so here we could say that the current in one case, again, is delta V over R, so 12 volts over 9 ohms in one case, or 12 volts over 3 ohms in the other case, and go from there. And so here, so 12 divided by 9 is 1.33. So, and 12 divided by 3, we can do it in our heads, and that's 4.0 amps. And so looking here, we have got a total, if we work it out, oh, I guess we should have done it at this level as well, and we could have done 12 over 9 fourths. And if you do a total delta V of 12 over 9 fourths, you get 5 1/3, 16 thirds, or in this case, 5.33 amps. And what that means in this case, this 5.33 amps would correspond to 5.33 amps leaving the positive terminal of the battery. But once it reaches this junction, it splits in two. And in this case, through the 9 ohm resistor, we found out that we've got 1.33 amps. So traveling down here, let's make that look a little better. Maybe I can write that sideways so that looks a little better. And then through the 3 ohm resistor, we've got 4 amps going this way. And so 1.33 amps this way, 4 amps this way, and notice those add up to 5.33 amps, as they should. The current that goes into that junction has to be perfectly matched by the current going out of the junction. You can't just like lose some of that charge. Cool, there's one other way we could have approached this as well, and it's common to go this route as well, and we might have to. And the reason being is that, one, we could reason out on such a simple circuit that it was a 12 volt drop on either one of these. Okay. So that's not always going to be something that's readily apparent. It might be something you can figure out, but it's going to be extra work with more complex circuits. So the other way you could go about looking at this is you could go back to this 12 volts and the equivalent resistance of 9/4 ohms. So let's start from there real quick. And we'd say that I equals that 12 volts over that equivalent resistance of 9/4 ohms. And that is where we'd get that 5.33 amps. Okay. And again, that would be working our way back, the current leaving the positive terminal of the battery. And it's going to be the total current that leaves that junction on two different pathways. But how do we figure out how much is leaving on those two different pathways? Okay, well, in this case, we know it has to add up to 5.33 amps. So, but we can kind of break it up into parts. Now, you might have heard the phrase the path of least resistance or the path of less resistance. So, and it comes from this actually. So current prefers to follow the path of less resistance. If you recall, we called it resistance because it's resisting the flow of charge, resisting current. Well, in this case, this current has an option of going through a 9 ohm resistor or going through a 3 ohm resistor, and it will preferentially choose the path of less resistance. It's going to choose the 3 ohm resistor. And in fact, because this 3 ohm resistor is only 1/3 of the 9 ohm resistor, you're going to get 3 times more current. Again, there's an inverse relationship between current and resistance. 1/3 of the resistance gets 3 times as much current. And so the current here, this 5.33 amps, 3 times more passes through the 3 ohm resistor than the 9 ohm resistor. If you look, 4 amps is exactly triple, 3 times more than the 1.33 amps that's passing through right here. Now here we already had the numbers and we're kind of verifying that after the fact. How would you actually calculate it? Well, if you figured out this was a 3-to-1 ratio, so in this case with the 3-to-1 ratio being in resistance, you'd have to know that the actual 3-to-1 ratio would be 3-to-1 in terms of the current. It's the opposite ratio. 3 times more goes through the smaller resistance, 1/3 as much goes through the larger resistance. So that's backwards in that sense. And in this case, with a 3-to-1 ratio, that's 3 out of 4 parts going through this path, only 1 out of a total of 4 parts going through this path. So, and if you don't like that reasoning and breaking it to 3-to-1 ratio, and maybe it's not always going to be a nice round number that you can reduce it down to, you could always just say it's, for this pathway over here, we're going to use this in the numerator. 3 out of a total of 9 plus 3. Times that 5.33 amps. So, and that's going to be the part that's going through the other side of the circuit. So, and then to get the opposite one, we'd use 9 out of a total of 9 plus 3. So times that total of 5.33 amps. And notice that 3 out of 12 is the same thing as 1/4. 9 out of 12 is the same thing as 3/4. And again, I looked at it as a 3-to-1 ratio, and 3-to-1 means 4 total parts. 3/4 of it, again, going through this side. This is just my other way of coming to the conclusion of 3/4 of it, 9 out of 12 parts. So 1 out of the 4 parts is going to go through this side. This is my way of figuring that out. And again, it's 3 out of the 12 parts. But again, you have to remember that because of the inverse relationship between current and resistance, so that even though this is the higher resistance, and you might think that it represents 9/12 of the resistance, if you will. So over here is where you're going to get 9/12 of the current. And that's why we're going to multiply the 5.33 amps by 9/12 to get this 4 amps right here. And that's exactly what it comes out to. 9/12 times 5.33 does indeed come out to 4.0 amps. So in 3/12 or 1/4 times 5.33 comes out to 1.33 amps. And this would have been the other approach to take. And sometimes we're going to have to go this route. It seems a little harder. So, but again, we got lucky on such a simple circuit that we knew the potential drop across each one of these. And we could just say, it's 12 volts across this one, it's 12 volts across this one. Life is good. We won't always be so fortunate in other cases, as we'll see. All right, one last thing to notice here. If you notice, when I had a 9 ohm and a 3 ohm resistor in series, the equivalent resistance was larger than either one separately. So when you have resistors in series, the equivalent resistance is larger. It gets bigger. But if you notice here, we had 9 ohms and 3 ohms, but the equivalent resistance here is going to be just 2.25 ohms. When you have resistors in series, in parallel, when you have resistors in parallel, the equivalent resistance is actually smaller than either of the resistors. So having resistors in series, the overall resistance in the circuit, the equivalent resistance of the circuit goes up. When you have resistors in parallel, the overall resistance or equivalent resistance of the circuit's going to go down. That's something worth filing away. Sometimes you get some more conceptual problems where they give you like light bulbs in a circuit and how brightly will it shine? Well, the more current it gets, the more power it's going to be dissipated, so the more brightly it's going to shine. And you have to realize that, oh, well, if over here in parallel the resistance actually goes down, that's going to lead to more current and brighter light bulbs. Whereas here, when you add resistors in series, that's going to lead to greater resistance, less current, and less power being dissipated, and these would be less bright light bulbs if that's what they were. So that sort of thing. So a good thing to file away. So resistors in series lead to a greater overall resistance, a greater equivalent resistance. Resistors in parallel lead to a lower equivalent resistance instead. So now we're going to deal with a little more complex circuit here. And so it turns out in the next chapter, we're going to deal with what we call complex DC circuits or direct current circuits. And this is technically not going to be considered one of the complex ones. We're going to find out that the complex ones we deal with in the next chapter might have multiple batteries, and that makes things much more challenging than this one right here. With just a single EMF source or battery, we can actually usually reduce this down to a single equivalent resistance, and life is good. With the more complex circuits where we have multiple sources of EMF, it's not always going to be so straightforward. We'll find out we've got to apply what we call Kirchhoff's rules and things of this sort. And the process is much more complicated than what we're going to do here. So I realize this looks fairly complex compared to what we've just done, but this is technically not considered a complex circuit. I just want to get that out of the way. The question here we have is, calculate the equivalent resistance of the following circuit, calculate the voltage drop and current through each of the 4 resistors. And if we wanted to, we could also calculate the power dissipated in any one of these 4 resistors as well. All right. So first thing we want is the equivalent resistance. We're going to have to do this in steps, it turns out. And sometimes it's convenient for identifying junctions. And if we look here, if we go around starting at the positive terminal and work our way around, there's our first junction where the current would have to split into alternate pathways and it would join right back up here. And so from this junction to this junction, there's 2 alternate pathways. And when you have alternate pathways, it tells you those circuit elements are arranged in parallel. So we can definitely combine those 2 in parallel fashion. So then the current's going to flow through this little, joins back together and flows through this little region here until it reaches this junction right here. And it can split back up into 2 pathways before rejoining right back in this junction. And so once again, when you've got alternate pathways between junctions, those are in parallel, and we can combine those 2 in our next iteration of this diagram here. And so the next iteration of this diagram is going to look like so. So we still got a 12-volt power source, but then these 2 combined, we're going to get an equivalent resistance between those 2. And then these 2 combined in parallel, we're going to get an equivalent resistance as well. This is fairly common. Now again, we're combining them in parallel in both cases, so we're going to have to add them as reciprocals. But again, it's really common to have 2 of them combined in parallel. And so again, memorizing that, oh, when it's just 2 in parallel, yeah, I can do 1/4 plus 1/2 equals 1 over the equivalent resistance, find a common denominator. But when there's just 2, I can also do R1 times R2 all over R1 plus R2 and make my life easier. And so in this case, 4 times 2 over 4 plus 2 is 8 over 6. And 8 over 6 is 1 1/3. And so the equivalent resistance here, so in 8 over 6, I'm just going to leave it as 4 over 3 ohms. So, or I could have written it as 1.33 ohms. Same thing here with these 2 in parallel. Again, I could do 1 over 9 plus 1 over 3 equals 1 over the equivalent resistance. In fact, those are the numbers we just had in the last example. But in this case, again, it's easier for me with 2 of them to get in the habit of just being 9 times 3 over 9 plus 3. 9 times 3 is 27, 9 plus 3 is 12. And if you recall, 27 over 12 reduced down to 9 over 4 ohms. And so now we've reduced our circuit down, but notice we don't still have just 1 equivalent resistance. We couldn't do it in a single step. And so the question is now, how do we reduce this down even further? Well, in this case, as the current leaves our battery now, it passes through this resistor, and there's no junctions. Any current going through this resistor has to go through this resistor. They are related in series. And so now we're going to combine these in series to finally get down to a circuit with just a single equivalent resistance. And so in this case, 4/3 plus 9/4. And we could get common denominators and everything, but I'm just going to let our calculator do the heavy lifting for us. So 4/3 plus 9/4. It's going to get us 3.58. as our equivalent resistance. Okay, so first question answered. What's the equivalent resistance of the circuit? It is 3.58 ohms. And now the question is calculate the equivalent resistance and then calculate the voltage drop and current through each of the 4 resistors. And the way you work this, so we had to get down to this single equivalent resistance diagram in multiple steps. What you're going to do now is, going backwards, You're going to first deal with your most reduced diagram and then work your way back up till you're back to the original diagram dealing with the actual resistors as they exist. But you have to kind of work it backwards from here on out. And so in this last diagram, we know delta V and we know R, so we should be able to calculate the current I. And that's where we'll start. So in this case, we've got I equals delta V over R, which in this case is 12 volts over 3.58 ohms. And again, we'll let our calculator do the heavy lifting. 12 divided by 3.58 is 3.35 amps. Okay, so if we looked at it here, we've got 3.35 amps going through the circuit. Now what that means going up to the next diagram is that we've got 3.35 amps leaving the positive terminal of the battery here, but technically we've also got 3.35 amps leaving the positive terminal of the battery there as well. Now in this diagram, that 3.35 amps has to go through that resistor and that resistor, i.e. equivalent resistor, if you will, so before coming back to the negative terminal. And so we could use that, since we know the resistance of each of these equivalent resistors, and now the current flowing through them, we could now use Ohm's law to find delta V. So we've got two parts of this calculation. Delta V equals IR. So in this case, in either case, it's going to be 3.35 amps. In the first case, times 4/3 ohms. And in the second case, times 9/4 ohms. Let's see what these work out to be. So 3.35 times 4 over 3 gets us 4.47 volts. And then times 9/4, so 3.35 times 9 over 4 gets us 7.54. And what you'll see here is that if you add these two together, you're going to get almost exactly 12 volts. So, and again, we're going to find out that Kirchhoff had a loop rule that around any loop of any circuit diagram you have, the voltage increases by batteries are going to be matched by voltage drops across resistors. And so we got a 12 volt increase here matched by a 4.47 volt drop here and a 7.54 volt drop right here. Okay. Now that's important because, again, these resistors don't actually exist. They're equivalent resistances representing combinations of resistors on the original diagram. But what we do know is that if this is a 4.47 volt drop across this equivalent resistance right here, what that means is that from this junction to this junction, that's what corresponds to the 4.47 volt drop. So, and then again, if it's a 7.54 volt drop across this equivalent resistance, what that means is that from this junction to this junction, that's going to correspond to the 7.54 volt drop. And if you recall, for combinations of resistors in parallel, the potential drop across either pathway is exactly the same. And so it turns out the potential drop across this 4 ohm resistor is 4.47 volts, just like it is on this side across the 2 ohm resistor, 4.47 volts, just like it was across the equivalent resistance of the combination of the two. Same thing down here, across the 9/4 ohm equivalent resistance was a potential drop of 7.54 volts. That means between this junction and this junction, it's a 7.54 volt drop whether I take the pathway around the 9 ohm resistor or the pathway around the 3 ohm resistor. And so now we found the potential drop across all 4 of the resistors. And from there, we could go further and say, okay, well, if we know the potential drop across all 4, we know their resistances, then we could use Ohm's law to calculate the current through all 4 as well. And that's what we're going to do, but actually, I think we can do this. So in this case, we'll use, again, I equals delta V over R. And so we'll have the 4 ohm resistor, the 2 ohm resistor, the 9 ohm resistor, and the 3 ohm resistor. All right, for the 4 ohm resistor, we can have I equals 4.47 volts. delta V over the 4 ohms. For the 2 ohm resistor, it's going to be 4.47 volts over the 2.0 ohms. For the 9 ohm resistor, it's going to be now a 7.54 volt drop over the 9.0 ohms. And finally, for the last one, the 3 ohm resistor, it's going to be the 7.54 volt drop over the 3.0 ohms. Let's see if I line this up just a little bit better. Cool, I'll let the calculator do our heavy lifting yet again. And so first, 4.47 divided by 4 is going to be 1.1175. I'm going to round that to 1.12 amps in this case. In fact, actually I only need 2 sig figs, so I'm going to round that to 1.1 amps in this case. All right, and then 4.47 divided by 2 is going to get us 2.235, which will round to 2.2 amps. All right, 7.54 divided by 9 is going to get us 0.837, which I'll round to 0.84 amps. Then 7.54 divided by 3 equals 2.5133, so 2.5 and 2 sig figs amps. All right, so let's look at how this works now. We'd figured out long ago that there was 3.35 amps of current leaving the battery. And when that current reaches this junction, it's going to split into 2 directions here. And we can see that through the 4 ohm resistor, 1.1 amps is going this way. So, and then through the 2 ohm resistor, 2.2 amps is going this way. And what do those add up to total? Well, it adds up right close to 3.35 amps. In this case, if we carried one more decimal place, we'd see it, but right around 3.3 amps, as it should. The current flowing into that junction should equal the current flowing out of that junction. And it's going to join back together so that the current flowing from this junction to this one is also, again, that 3.35 amps. And it's going to split into part this way. It's going to split into part this way. And again, the total between those two should still add up to 3.35 amps. Through the 9 ohm resistor, it's 0.84 amps. Through the 3 ohm resistor, it's 2.5 amps. And 2.5 plus 0.84 or 0.8 adds up to 3.3 amps yet again. It works out the way it should. Now, we could have approached this one other way, and we could have said, well, you know, I've got 3.35 amps flowing into that junction. And with the 4 ohm to 2 ohm ratio, so I could see that this is half the resistance, so it should get double the current. And double means a 2-to-1 ratio, which means 2/3, 2 out of 3 parts, 2/3 of it should go through this side, 1/3 through this side. And if we multiply 3.3 amps, if we rounded it down for the sake of making the numbers work here anyways, if we took 3.3 amps, 2/3, that is 2.2 amps. 1/3 is 1.1 amp. Similar down here, we got again the 3.3 amps and some change flowing into this junction. And again, this is just 1/3 of the resistance of the 9 ohms. So 3 ohms represents 1/3 of the resistance of 9 ohms. You have again this 3-to-1 ratio. And 1/3 of the resistance means 3 times the current. Again, that 3-to-1 ratio. Or maybe I should say 3-to-1 if I put it on the right sides here. So 3-to-1 means 3/4 of the current is going to go through this side. Guess what 3/4 of 3.3 amps is? It's 2.5 amps. The other 1/4 goes through this side. What does that equal to? 0.84 amps. So another way you could have gone figuring out that current. So there's often more than one way to skin a cat and approach these problems. You just want to pick the one that's easiest for you. If you look at Ohm's law, delta V equals IR. If you know any of those two for any single resistor, you can get the third one. And notice we could go from here and now say, well, what if I wanted power for any of these resistors, the power dissipated? Well, again, if you recall, power equals delta V times I, or delta V squared over R, or I squared times R. And if you know any two of the 3 properties, you've got an equation for power that will allow you to calculate it in one way, shape, or form. This is kind of as hard as it gets, truth be told, until we get to the more complex DC circuits in the next chapter. If you found this lesson helpful, consider giving it a like. Happy studying.